Hey guys, it's Mr. Haddock here, and today we will be reviewing the scientific method. You will need a piece of paper and a pencil in order to take notes on this PowerPoint. If at any time I am moving too fast during the PowerPoint, please feel free to pause the video on a particular slide so you can finish copying the notes. The first step to the scientific method is to state the problem in the form of a question. It is extremely important to begin with a solid problem or a question. If you do not start your search with a question or a problem that is testable, then you will struggle to find a valid answer in your quest for solving this problem or answering this question. There are three things that a good question possesses. The first is that it can be examined. The second is that it's measurable. And the third is that it can be analyzed. Choose a problem that you do not know the answer to and a problem that you can work with. So don't pick something that is well out of your wheelhouse of understanding, but don't pick something that you already know the answer to when going through the scientific method. Some examples of testable questions that are good would be, does the life of a light bulb depend on its wattage? What are the effects of caffeine on the respiratory rates of cockroaches? And how do wing shapes affect the lift of airplanes? Those are all three great examples of questions that are testable using the scientific method. Step 2 is research the problem. Research is very, very important in that it can do a lot of your heavy lifting with someone might have already done this experiment and found an answer, so all you would have to do is repeat the experiment, or maybe it gives you insight into how you want to design your own experiment. Research is arguably the most important part of the scientific method. If you have solid research, it can make your project even better, or your experiment, and it could absolutely make an experiment fall apart if not done properly. When you do research, you want to pull from a wide variety of sources. You want to pull from library books, you want to pull from newspapers, magazines, scientific journals, the internet. Luckily, most of this stuff is now online, so you don't necessarily have to go multiple places to access things like magazines and newspapers. Scientists rely heavily on the scientific method because there are so many variables to consider, and any one of them could affect the result of an experiment. And that is why research is so important, so you know what variables to control for in your experiment while you're designing it. Step 3 is to form a hypothesis. Hypothesis, I'm sure you've heard the term an educated guess. Well, that doesn't make sense in my opinion. You can't be educated on a particular topic and just guess, right? So my definition for hypothesis is an educated prediction or explanation about a possible solution or answer to your problem or question. Developing a good, solid hypothesis is probably the most challenging part for a lot of young students and a lot of young aspiring scientists, because your experiment is completely surrounded by your hypothesis and testing it. It makes it very difficult to perform a solid experiment without a solid hypothesis. So just like that fourth bullet says, if a hypothesis doesn't make sense, the whole project won't make sense. So that's why it is very important for the hypothesis to be very strong. When forming a hypothesis, the simpler the better. Make it precise and measurable. We usually recommend that students write their hypothesis in an if-then statement. If this happens or if this occurs, then this will happen. That makes it a little bit easier for students to consider or gives them structure to write a quality hypothesis. Step 4 is to write down the procedures. Writing down the procedures allows other scientists to look at your experiment and reproduce it. So you want to be specific in writing procedures when you have that opportunity. You want to make sure that anyone could pick it up and be able to redo your experiment in the same way that you did. The more unclear the procedures are, the less likely someone else is willing to confirm your findings. Step 5 is perform your experiment to test your hypothesis. The number one rule for testing a hypothesis is to always follow the written procedures. Don't deviate. Don't think that you have a better way. Follow what the written procedures say. And the reason why is because if you go off, then and your results are different than someone else, then it might be a little bit confusing on trying to figure out what actually caused it. Was it your change, or was it because of the initial procedures? Alleviate any confusion and stick to the written procedures. Now, when you perform an experiment, you always want to have a control group. These are the groups or the things that are not being tested on, that are not receiving the treatment, that are not receiving your variable that you are testing. And the reason why is it gives you something to compare to. It gives you a baseline. Variables are the factors in an experiment that are being tested. It is extremely important during an experiment that you test one variable at a time. When you test more than one variable, complications can arise, and it can be very difficult to identify what is actually causing the change. And then, of course, your experimental group is the group that is being tested by changing one variable. And then you would compare your experimental group's results to your control group results. Step 6 is to observe and record all the results. While you're performing an experiment, scientists tend to keep a journal, and they are very, very detailed in writing down their observations and data. The more data, the better for them. And all data is not created equal, but at least if you wrote it down, you have access to it, and you can determine at a later time whether or not it is worth studying farther, or whether or not you should just get rid of that data and not use it in your conclusion. So while observing and recording your results, be sure to be very specific and very observant during experiments. Step 7 is to interpret the data. Usually the interpretation of the data is to make it easier to identify patterns or themes or anything, or even to help digest a massive amount of data. I don't know if you guys have seen a spreadsheet completely full of numbers, but that is very intimidating, whereas something like this pie chart is a lot more easy to understand when understanding data. And then the last thing is the conclusion. Step 8 is the conclusion. This is how you communicate your findings to other people. So you want to answer the questions: what happened? Was it what you expected? Did the results agree or disagree with your hypothesis? And was the original question that you posed answered? And whether or not your hypothesis is correct is irrelevant in a lot of cases, but rather just gaining knowledge is what is the key fundamental pillar of science. Now, the way I just described the scientific method is very, very rigid and structured, and you must follow these steps. That is not how the real scientific method goes. The real scientific method isn't necessarily a strict ladder or strict steps, but rather it looks something more like this, where scientists are exploring and discovering and testing those ideas, and then going out to communicate, and then coming back to test more ideas. And then they're also weighing the benefits with the outcomes to their ideas, and going back and testing them, and just they're constantly going in and out of the scientific method, and in different stages of it, depending on how their experiments, depending on how their results go. So this is what the real scientific method looks like, although I did try and simplify it for you, so that it is a little bit more digestible for young scientists like you to understand. So hopefully you were able to copy down all those notes. What you will do next is in the Canvas. So have a great rest of your class, and I will see you soon.